For example, magnesium is only found in EcoRB, a restriction enzyme, but EcoRB does contain a magnesium. So we find magnesium in many different enzymes. For example, hexokinase, right? Hexokinase is important. We'll see this is the first enzyme that we're going to encounter when we talk about glycolysis. Magnesium 2+, right, this divalent cation, we find in almost every enzyme that deals with a nucleoside triphosphate, most specifically ATP. And hexokinase deals with ATP. Hexokinase takes a glucose and an ATP, yields an ADP, and it has transferred a phosphoryl group from ATP onto glucose, generating glucose 6-phosphate. So hexokinase belongs to this class here. Transferases, right? So it transfers a phosphoryl group from ATP onto glucose. And we have other examples of metals that are found in different enzymes, right? So many enzymes, okay? Many enzymes require these cofactors. And cofactors can either be vitamin-derived coenzymes, which, by the way, is why it's so important to get a sufficient amount of vitamins. The reason being we cannot synthesize these de novo. We have to alter vitamins in order to generate these cofactors, and without these cofactors, many metabolic enzymes cannot be formed. All right. Now, enzymes can transform energy from one form to another. Okay, they can harness the energy. For example, they can harness the energy from oxidation as chemical potential energy. They can use chemical potential energy then to do work. Okay, what this work is depends. That work could be moving molecules against their concentration gradient, or it could be, diamine walking along actin filaments, or whatever, right? Point is that they can transform potential energy into kinetic energy or whatever, right? So they're literally energy transducers. What they do with that energy depends on what that enzyme is doing. All right, so let's look at the thermodynamics of enzyme catalyzed reactions, okay? So let's start again to review. The change in free energy, delta G, is dependent only on the free energy of the products and the reactants. Okay, so let's look here at our chart. Here we have free energy on the y-axis, reaction progress or reaction coordinate. We can think of it as kind of as time, we can say, on the x-axis, right? So we're starting with our substrate, right? So we have, say, substrate yields product, S yields P, and we start with 100% substrate. So we have a free energy. The free energy of the substrate is determined by the number and types and configuration of bonds in the substrate. So the free energy of the substrate is determined by the substrate. It is immutable. There's nothing that you can do that can change the free energy of this molecule or molecules that we're working with. It's just what it is. It's the starting point. The same is true for the product. Okay, so the product's free energy is determined again by the number, types, and the arrangement of bonds. It's immutable, so nothing we can do can change it. So the delta G for a given reaction, in this case S yields P, will always be the same, right? If we're starting with S and we're ending with P, delta G, the change in free energy from S to P, cannot change ever. Okay, it just can't, right? Now, why is it that we said, of course, that the change in free energy is negative, right? The reaction will proceed forward spontaneously. It's because the lower energy we have, the more stable the state that system is in. Right? So if we have a lower energy in the product minus a higher energy of the substrate, of course, the difference between those two will be less than 0. Okay? This means that our product state or our end state has a lower energy and is more stable than the initial state or the substrate state. Right? So again, the delta G tells us that the reaction can take place spontaneously. If delta G is negative, the reaction or process must take place, will always take place, but it doesn't tell you anything about the rate at which it will take place. We'll get to that in a minute. Now, if delta G equals 0, right, what does that mean? That means that the system is in equilibrium. And what do we mean by that? Right? Who remembers what equilibrium means? The rate of the forward and of the reverse reaction are the same, right? What does this imply? Right? That means that P is being turned into S, so we have a positive change that way, at the same rate that S is being converted to B, so we have a negative change that direction. But they're of the same magnitude, so they cancel out. Delta G is 0, right? So when delta G of the system is 0, the system is at equilibrium. Now again, delta G tells us nothing about the rate or speed of the reaction, okay? Here, we know that the reaction will proceed forward, right? It must proceed forward. It will always proceed forward until we reach some equilibrium, okay? But it doesn't tell us anything about how long it will take to reach that equilibrium. It could be seconds, it could be minutes, it could be centuries, okay? So going back to the example of a peptide bond, again, there's a delta G of between -15, -20 kilojoules per mole, but how long does it take for a peptide bond to be hydrolyzed? Or for a mole of peptide bonds to be hydrolyzed? A mole of peptide bonds to be hydrolyzed takes over 100 years to be hydrolyzed. It will happen, right? So if we had long enough lifespan and we had nothing to do but watch this beaker of peptide bonds, we would see eventually that a protein degrades in an aqueous solution. It will always, right? But it happens very slowly, luckily for us, meaning that on a time scale that is relevant, okay, a peptide bond is kinetically stable. Yes, it will degrade, but not on a time scale that matters to us. All right, now delta G naught prime is directly related to the equilibrium constant, KEQ, right? So let's look at our hypothetical reaction here. A plus B yields C plus D. We can put together this equation here. Delta G, the actual change in free energy, is equal to the standard change in free energy, delta G naught prime. So this is meaning that everything is at 1 molar or 1 atmosphere at 25 degrees Celsius, and that we pH is 7.0. That's what the prime denotes here, the pH is 7.0. So the actual change in free energy equals the standard change in free energy plus RT ln Q. Q, of course, being the reaction quotient, right? So it's the concentration of C and D multiplied together divided by the concentration of A and B multiplied together in this case, right? Now, let's see what happens at equilibrium. Again, remember, at equilibrium, delta G is 0, right? So let's plug in 0. We solve, and we get delta G naught prime equals negative RT ln Q. But now, Q is something particular, right? Because we're at equilibrium, now it's not the reaction quotient, it's the equilibrium constant, right? So we can rewrite this then to say that the standard change in free energy, delta G naught prime, equals negative RT ln K prime EQ, all right? So there's a relationship then between delta G naught prime and K prime EQ. Now let's go back, right? So what we're looking at over here, okay, this is the standard change in free energy. Again, that cannot change because the conditions are always the same. Everything's at 1 molar, everything's at 1 atmosphere at pH 7.5. If we now add an enzyme here, right? An enzyme that can catalyze a reaction S yields P, right? Is the delta G naught prime going to change? Is S going to change? Is there anything different about what we're starting with in an enzyme catalyzed reaction? No, we're still starting with S, right? Is there anything different about P at the end? No, right? We're still ending with P. We're just doing it faster. Now, there's nothing different about P and there's nothing different about S. Is there anything different about delta G naught prime? Right, no. So delta G naught prime cannot change whether it's catalyzed or uncatalyzed. So coming back here, delta G naught prime equals negative R, right? What's R? Universal gas constant, right? So this is constant in the universe. Unless we're changing the laws of physics, this is not going to change. T, right? This is just the temperature. So let's say that we're doing it at the same temperature, catalyzed versus uncatalyzed. Ln K prime EQ, right? So this isn't changing, and this isn't changing, and this isn't changing. Can K prime EQ change? Why do you think? You were nodding your head. Not sure. Okay. Who else? If delta G naught prime isn't changing, will K prime EQ change?
Oh, no.
You can change the molarities? Well,
I guess the ratio is the same.
Right, the ratio stays the same because we reach the same equilibrium, right? The equilibrium is the equilibrium of this reaction, right? But even mathematically, if we're not changing this, or this, then this can't change. Because if we change this, but we're not changing either one of these, well then the result, delta G naught prime must change, but we know that we can't change it, right? So there is a strict relationship between delta G naught prime, here we see in kilojoules per mole, and K prime EQ, right? This is always true, the relationship is always the same at 25 degrees Celsius, or at any given temperature, right? Now, as we might imagine, okay, if K prime EQ is 1, right, that means that delta G naught prime is 0. So we have reached, or the reaction is not going to go forward or backwards. If K prime EQ is less than 1, let's see what that means. That means that A or B, or A times B, is bigger than C times D, meaning that we have more reactants than we do products. So the reaction is not going forward, right? If we have more reactants than we do products at equilibrium. So we have less than 1 as K prime EQ, well, delta G, as we expect, is positive, means that the reaction didn't go forward. If K prime EQ is higher than 1, this means that C times D is greater than A times B, meaning we have more product than we do reactant, so the reaction went forward, and as we expect, the delta G naught prime for those is negative, right? So there's a strict relationship between free energy as in under standard conditions and the equilibrium of the reaction, which is very useful to us. Now, delta G naught prime is a bit of a red herring, because we go back here, right? This equation uses delta G naught prime, but delta G naught prime, again, remember, is everything under standard conditions. So again, 1 molar, 1 atmosphere, 25 degrees Celsius, pH 7.0. So right off the bat, there's 2 issues with using standard conditions. Right off the bat, okay? First, what? Why can't we use delta G naught prime to determine if reaction will proceed forward biologically? Okay, biological pH is 7.4, let's call it 7. But that's a good catch. So really there's 3. So what are the other 2? Nothing is at 1 molar in our body, right? What else? Huh? Okay, yeah, not at 1 ATM, not at 1 molar. This is all correct. There's one other problem. Right, what temperature are we at? 37, right? So we can't use delta G naught prime because we don't exist under standard conditions. So what determines if a reaction will actually proceed forward under real conditions is the actual change in free energy. That is delta G not standard, right? And that is this equation here. So delta G equals delta G naught prime plus RTLN cubed, which is just the ratio of products and reactants. So for example, all right, let's go to this practice here. At equilibrium, the ratio of glyceraldehyde to phosphate to dihydroxyacetone phosphate is 0.0475. Okay? So what is this? We are looking at this reaction. Dihydroxyacetone phosphate. Right? This is catalyzed by triose phosphate isomerase in step 5 or 6 of glycolysis. Okay? So Q in this case is what? The ratio of glyceraldehyde phosphate to dihydroxyacetone phosphate. Okay? Let's see what's going on. So the ratio of GAP to GHAP is 0.0475. Right? So K prime EQ is 0.0475. All right. So what is the standard change in free energy? We want to know if under physiological conditions this reaction is going to proceed forward. Right? And why do we care? Or how do we do that? Right? So is this going to proceed forward? Well, we need the actual change in free energy. Right? So we need delta G naught prime plus RTLN P over R. So we say that the concentration of products and reactants are 2 times 10 to the minus 14 and 3 times 10 to the minus 6. So we can plug those in here, but we don't know delta G naught prime. But we do know K prime EQ, right? And we know then, because of the relationship between them, if we know one, we know the other. Delta G naught prime equals negative RT ln K prime EQ. So K prime EQ equals E up to the negative delta G naught prime divided by RT. Okay, we do all that, we get positive 7.53 kilojoules per mole, right? R, you should memorize, that's 0.0083145 kilojoules per mole. Right, so we want to make sure we convert our temperature into Kelvin, so 25 degrees Celsius, that's 298 Kelvin. This gives us positive 7.53 kilojoules per mole, as we expect, because the ratio of product to reactant is less than 1. So this reaction doesn't proceed forward, okay? So the delta G naught prime should be positive. Now let's see if this will proceed forward under physiological conditions, right? So in this case, the concentration of glyceraldehyde 3-phosphate is 3 times 10 to the minus 6 molar, put that up there. Concentration of DHAP is 2 times 10 to the minus 4 molar, put that right here. R, we know, 0.0083145 kilojoules per mole volt, or per mole Kelvin rather. Temperature, in this case, is going to be what? Is it going to be 298, or is it going to be something else? What's the temperature of our bodies? You can answer in American units. 98.6 degrees. How many of you are trying to be doctors right now? Okay, 98.6, 37 degrees Celsius, add that to 273, we get 310 Kelvin, right? So 310 Kelvin times 0.0083145 kilojoules per mole Kelvin times ln of Q plus positive 7.53 kilojoules per mole, since we just calculated that to be delta G naught prime, and now we get an actual change in free energy of negative 2.89 kilojoules per mole. So under physiologically relevant conditions, the actual change in free energy is negative, and this reaction will proceed forward, right? So this is how pathways work, essentially, right? A pathway removes product from reaction 1, okay, by using it as a substrate in reaction 2, right? So we keep the concentration of products artificially low, and because we're grabbing it, we're getting a steady source of substrate for reaction 2 from reaction 1, that increases the concentration of substrate there. So it pushes all of the reactions forward, okay? And that's what's happening here, even though the conversion from dihydroxyacetone phosphate to glyceraldehyde 3-phosphate doesn't proceed normally. We need it to proceed. So how do we get it to proceed? Well, we're getting a steady source of dihydroxyacetone phosphate from glycolysis from the previous step. And the subsequent step is removing glyceraldehyde 3-phosphate by using it in the subsequent step. So this leads to an imbalance in how much we have, right? So this pushes the reaction forward, leading to a negative actual change in free energy. So it's the actual delta G, not the delta G naught prime, that determines if a reaction will proceed forward, right? Now, enzymes alter, again, only reaction rate and not equilibrium. So if we look over here, we see we're measuring, right, what's the velocity, what's the rate of a reaction, is how much product is being formed per time, right? So product per time, so the slope here is the rate. For an enzyme uncatalyzed reaction, right, it would say first order. Well, what we get is just a linear line, okay? Which is redundant, linear line, obviously, but we get the line where the slope is equal to the rate or the velocity. For an enzyme uncatalyzed reaction, again, that's just linear. And why is it linear? Well, if we think about what a reaction looks like and how to calculate the velocity of a reaction. So again, we have A yields B, right? Well, these are each going to have their own rate constants, right? So little k1, let's say, or forward, and little k reverse, okay? So the velocity of this reaction is just equal to the rate constant times the concentration of K, right? And what is the velocity? Is equal to the amount of product being formed per time. So we can see why for a first order reaction, all we get is a straight line. Now for an enzyme uncatalyzed, or for an enzyme catalyzed reaction rather, right, what we get is a hyperbolic plot here, right? So you see, eventually we reach the same equilibrium, right? It just took the enzyme catalyzed reaction less time to get there, okay? Now, as we go forward into actually, some math here, let's just get something straight. So this is the velocity of the forward reaction, right? Now, what's going to be the velocity of the reverse reaction? Huh?
Is there reciprocal?
No.
Reverse. It's going to be reverse, right? Minimum concentration.
Yeah. All right, which brings us to something important that's going to be useful as we go further here, right? At equilibrium, what do we know about the velocities? Yeah, they're equal. The forward and reverse velocities are equal. So if we set these equal to each other, we say that K F times A equals K reverse times B. In other words, B over A equals what? KF over A reverse, right? And what is B over A at equilibrium? What do we call that? Yeah, just KEQ. So we see that we actually have two different ways to define KEQ. Obviously B over A at equilibrium, but that's also equal to the ratio of the forward and reverse rate constant. That's what we see over here. K equals B over A, also equals KF over KR. Now, let's go back again. Comparing an enzyme catalyzed reaction to an enzyme uncatalyzed reaction. Okay? Does the equilibrium change? No. Right? But what are we doing? We're increasing the rate of the reaction at any given concentration of substrate. So that means that we must be increasing this rate constant, Kf, right? Now let's say that a hypothetical enzyme increases the rate of a reaction 1,000-fold, right? So we're multiplying K forward by 1,000, right? So that's going to times the velocity by 1,000 at any given substrate concentration. What's going to happen to K then if we multiply Kf by 1,000? Huh? It's going to increase, right? By how much? About 1,000 times. Are we allowed to do that? No. Right? K can't change because delta G naught prime isn't changing. So how are we increasing Kf by, say, 1,000 times, or in some cases we saw 1 billion times? How are we increasing that while leaving K alone? Yeah.
Do you increase the reverse rate constant?
Right, you have to also increase the reverse rate constant, right? So if we increase the forward rate constant by 1,000, we increase the reverse rate constant by 1,000. This maintains K, maintains delta G naught prime, and this is exactly what enzymes do. They increase the rate of the forward and the reverse rate constant. So, we go back to our coordinate diagram, okay? We're still gonna have to get up here to transition state, right? And then fall down here or fall down here, and eventually reach the equilibrium. We have more here and more here. It's just, it's doing that much quicker, right? Forward and reverse. So it reaches the equilibrium much faster. All right, now what limits the rate of a reaction is not delta G naught prime as we've seen, okay? It's instead this here, this activation energy. And what is activation energy? Well, again, remember, if we have this reaction here, A yields B, we don't go straight from A to B. Instead, we must first achieve some unstable intermediate called the transition state. Okay, now this transition state doesn't exist for any appreciable amount of time, but it does exist, right? Because it's so high in energy that as soon as it exists, it then decomposes to form either product or substrate, right? So what does a catalyst do, and specifically what does an enzyme do? An enzyme reduces the amount of energy that we have to put in to the substrate to reach the transition state, right? So say going from, the substrate has an energy of say 50 kilojoules per mole, and the transition state has an energy of 150 kilojoules per mole. That means that we have to put in 50 kilojoules per mole to get from S to the transition state. That's our activation energy. What an enzyme does is it reduces the amount of energy that we have to put in. It lowers the activation energy. So say now instead of having to put in 50, right, the transition state coupled with an enzyme, right? So a transition state in an enzyme active site has a free energy of say 120. Right? So now we only have to find 20 kilojoules per mole as opposed to 50. The lower the activation energy, the lower the amount of energy that we have to put in to achieve the transition state, the faster the reaction will happen because we need to find less energy. Once we put in that energy, well now we're free to do whatever we want. Okay, so the activation energy, delta G double dagger, is equal to the free energy of the transition state minus the free energy of the substrate. And so what determines, how does an enzyme actually lower the activation energy? And how does it achieve that? Well, it achieves that by utilizing its active site. Okay, so if we think about an enzyme active site, okay, that's similar to the binding site in a receptor ligand situation. All right, and what is going on? Multiple weak bonds are going to be formed. So the example with trypsin and thrombin and papain, right? When the substrate binds to the enzyme, multiple interactions are formed. These could be hydrogen bonds, it could be ionic interactions, it could be van der Waals, they could be whatever, okay? Weak interactions. Now let's say, just for easiness sake, so let's look at three different states. We have the enzyme bound to the substrate. We have the enzyme bound to the transition state, right? And here we have what we call the binding energy, right? Binding energy. Let's just make our lives easier and say number of interactions, right? The more interactions we have, okay, the more energy is released, so the more stable it is, and the higher binding energy we have. So in this case, the more binding energy we have, the better, okay? And that is just another way of describing the types, orientations, and number of interactions between something and the enzyme. So let's say that the enzyme and substrate together, they form, let's say, 4 interactions, okay? This is enough to achieve specificity, let's say, right? But when the transition state is achieved, let's say that now it forms 6 interactions, right? So we formed 2 more interactions. And what happens in terms of energy when interactions are formed? Energy is released, and does that make it more stable or less stable? Is it good or bad when energy is released? Right, good. Right, more stable. So, by having the maximal interaction, not between enzyme and substrate, but between enzyme and transition state, okay, it provides some of the energy that we would have had to found as activation energy. So, the difference between here and here, we call that the binding energy, right? That's how much energy is being provided by the transition state binding well to the enzyme, okay? So that's the binding energy. And this is how, again, activation energy is lowered. Some of this energy is being provided by the enzyme, by forming these weak interactions with the transition state and stabilizing it. Now, that's not to say that the transition state is now stable. It still would immediately decompose into either product or substrate, but it just took less energy to get there, okay? And so here we see an example of an active site, okay? The coenzyme in this case is CAM4, or the substrate rather. The substrate is CAM4, and the active site of this enzyme here, okay, has valine, aspartate, phenylalanine, tyrosine, valine, leucine, all in its active site over here, along with a heme prosthetic group. this binds CAN4, the substrate, and binds it specifically. So it's forming a hydrogen bond over here, it's forming van der Waals interactions, forming coordinate covalent bonds, right? So it's forming bonds with the substrate. But now, when the substrate adopts its transition state, okay, it'll be able to form better interactions with all of these residues in the enzyme active site. And that's the binding energy. That's what lowers the activation energy. Right, so again, here's just more on the structure of the active site. The active site is made up of amino acid residues. They don't necessarily have to be near each other in the sequence of the protein. They have to be near each other in the three-dimensional tertiary structure of the protein, right? So that they are oriented in order to form these favorable weak interactions with the substrate and the transition state. So here's, for example, uracil in the binding pocket of a enzyme that bonds uracil. So we might have a threonine residue here, and this would form hydrogen bonds with the, let's say, this oxygen on carbon 2, this oxygen on carbon 6 down here, right, forming hydrogen bonds with the serine. So they're oriented in such a way that they're able to form these weak interactions. All right, let's skip this. Okay, so let's get to kinetics, right? So enzymes can be, enzyme kinetics, right, can be described in terms of changes in substrate concentration and product concentration, okay? So let's examine what we want to define as the rate of an enzyme catalyzed reaction, the velocity of an enzyme catalyzed reaction. Velocity is simply going to be equal to the change in substrate divided by the change in time. And this is going to be of the same magnitude, but of the opposite sign as the change in product over time. Right? So however much substrate we're losing, we're gaining as product. Right? If a reaction is simply S yields P. Now the velocity can also be thought of as we said before, the rate constant, the forward rate constant times the substrate concentration, and vice versa. Product concentration